So when we convert 2 into binary digits, that becomes 1 and 0. So here 1 is the carry and 0 is the sum. So how you, so the next part, that is we are going to discuss, that is half adder. So what is half adder? So half adder is nothing but it is a simple combinational circuit that performs simple addition of two numbers. So if we assume A and B as the input bits whose addition to be performed, the block diagram and the truth table of the half adder with A, B as the inputs and some carry as outputs can be tabulated as follows. So here we can see in the truth table, when we take input 0 and 0, and then it becomes sum becomes 0 and carry becomes 0. And when we take input 0 and 1, then sum becomes 1 and carry becomes 0. When we take input 0 and 1, then sum becomes 1 and carry becomes 0. When you take input A as 1 and B as 1, then sum becomes 0 and carry becomes 1. And it is look like similar as the truth table of the XOR gate. So here we can represent sum as the a logic diagram of the sum output is shown below, look like similar to the XOR gate. Now we also see here the carry of this truth table is look similar to the truth table of the AND gate. So we can also represent the logic diagram for the carry is similar to the AND gate. When we combine these two diagrams, so we can represent the whole logic diagram of the adder circuit in the single logic circuit, that is represented as this. When we take input A and B, then the sum is the XOR gate of XOR of the A and B, and the carry is the AND of the A and B. We will discuss about what is full adder. So full adder is the adder circuit which adds 3 inputs and produces 2 outputs. The first 2 inputs are similar like the half adder, and the third input here as the input carry, that is Cin, and the normal output here is S, which is nothing but sum, and the carry output which is represented by here Cout. So here we can see in the truth table, now we can take here 8 different inputs. So when we take input 0, 0, 0, so first we will add 0, then it becomes 0, and then again 0 will add to Cin 0, then the total sum is 0 and the carry is becomes 0. When we take input 0, 0, 1, so we can add 0 plus 0, that becomes 0, and again 0 plus 1, that becomes 1, and the carry is 0. When we take input 0, 1, 0, so 0 when we add 0 plus 1 becomes 1, and 1 plus 0 becomes sum is 1 and carry is 0. When we take a 0, 1, 1, so here 0 plus 1 becomes 1 and 1 plus 1 becomes 2, which is converted when we in binary, so 1, 0. So here 0 is the sum and 1 becomes carry. So when we take input 1, 0, 0, so when we add 1 plus 0, that is 1, and 1 plus 0, that is again 1, so sum is there 1 and carry becomes 0. When we take input 1, 0, 1, so when we add 1 plus 0, that is 1, and 1 plus 1, again here the carry is generated, so sum is 0 and carry becomes 1. So when we add, take input 1, 1, 0, when we add 1 plus 1, so here sum is 0 and carry is generated, so sum is 0, so 0 plus 0, again sum is 0 and carry is 1. When we take input 1, 1, 1, so here when we add 1, 1, 1, then here is sum is 0 and carry is 1, so again 0 plus 1 is sum is 0 and carry is 1 here. So here is we can see the logical expression for sum and logical expression for the Cout. So we can also deduce this logical expression from the help of K-map, which we'll further discuss in the class by sir. And we can also generate this thing by this simply minimal sum of expression. So we can see this here for the sum 1. So here A bar, B bar, and C input is C. Here we can represent is A bar, B bar, and C. And also the other sum, that is 1 here, that is the input is A, is 0, 1, and 0. So here we can take A is A bar, B and C in bar. So here we can represent A bar, B and C in bars. Rest all is represented by this. So when we reduce this expression, we can see in this equation we can take a common C in, and it is represented as this. Here you can also take common C bar. It is look like this. So here we can see that there is A bar, B bar plus AB, nothing but it is X NOT gate, and here is A bar B and plus AB bar is nothing but it is XOR gate. So its whole expression becomes again it is XOR gate. So XOR A, XOR B, XOR C. So here we can see this expression in our full adder logic diagram. So first we take input A and B, then XOR of A and B, then again we get output here, and again which XOR we can XOR becomes C in with the C in, then we get the sum part. And also similar we can see the logical expression for C out. The carry is C out is here becomes 1 is for input 0, 1, 1. So here we can see that A bar, B and C in. Bar, B and C in. So again, logic inputs, the carry is 1, that is 1, 0, 1. So we can there is A, B bar, C in. So rest we can also reduce by in this manner. We can also take here in common C in. So we can write the expression becomes A bar B plus AB bar, which is nothing but the logical expression of the XOR gate. So we can again represent as C in A XOR B. And in this here we can also take common of AB. Then we have the expression is C in plus C in bar. This is nothing but it is equals to 1. By the simple Boolean expression we can get. And when we represent a C out with the help of K-map, then we can get also a minimal expression that looks like this. So when we represent these things by the help of logic diagram, so here we can see that here the AND of A and B. So we can take the AND output of input of A and B, and again the AND of A, C, A or C in. So again we can take AND of A and C in, and again AND of B, C in, and the totally of the C out is we will get by the OR of all the inputs. So that's all from my part, and the next part discussed by the Sengupta sir. And
Yes, Anirban.
no sir, wait. So I will
Okay, you have.
yes sir.
Yeah, the VLAB part, I think. Yeah.
Yes. Now I will show the simulation part. So here we can come in the VLAB. So here first we go to the procedure.
We are unable to see anything.
Yeah, the
Are you
VLAB is
using
not
it?
visible.
Sir,
I think you have shared. Yeah.
Yeah. Now it is.
now you are seeing.
Yeah. Now it is. Now it is there.
Okay, sir. So here first we will go in the procedure part and follow the line by line steps. So first we will see the here step number 1. So first we will connect the power supply. So go to the circuits. So first we will connect the power supply, and we again here is the input A and input B. So for the first time both the input is become 0. Then we will check the output. So here we can see the when the input becomes 0, 0, then the sum becomes 0 and carry becomes 0. Here we can see in the circuit diagram. Here the 7486 nothing but is the represented is the XOR gate. 7486 is the IC pin number which represent the XOR gate, and 740 is the IC pin number of AND gate. Each contains internal 4 XOR gates, and 7408 contains internal 4 AND gate. So again we come here in the input part. When we give input 0 and 1, for giving input 1 we place just simply here, and for the input 0, 1 we can see here we get sum as 1. So we can we can get, then we can see here in the truth table for 0 1 we can get sum as 1 and carry becomes 0. Again we will see for the input 1 0, again we get the sum as 1 and carry becomes 0. So when we press here add, so we can see here for the input 1 0 we can get sum becomes 1 and carry becomes 0. So for the again for the input 1 1 we see here the sums becomes 0 and the carry becomes 1. So 1 1 becomes sum is 2, so which convert in binary digit, that is 1 0. So 0 is the sum and carry is 1. So here simply press add button. So here you can see that for the input 1 1 we can get sum becomes 0 and carry becomes 1. We can see here also the simulated part 2, nothing but we will check the truth table for the input and output. Let's say for the input 0 and for the other input 0. So we can put here for the input 0 0 the sum becomes 0 and the carry becomes also 0. So when you press here check, then it shows we will for the input 0 0 we get the correct output here, that is sum is 0 and the carry is 0 also. So let's say when we press here for the 0 0, if we type here the sum is 1, then we will check, then it shows incorrect. So it's just the simulated part 2 is just cross checking of truth table. So again similar full adder is also look like similar as the half adder. Here we can see the 3 inputs, that is input A, input B and the C input. So here we also follow the same procedure. First we connect the power supply and then again here we can give the 8 different inputs. So first let's say for the inputs 0 0 and 0, then we will press the add button. Then we will here see in the truth table for the input 0 0 0 we can get the sum is 0 and the carry out is 0. Let's say for the another input we will check for the input 0 0 and 1. So for the 0 0 1 we can see here in the sum here the sum is 1 and the carry out is 0. So we can see for the input 0 0 1 the carry the sum is 1 here and the carry out is 0. So here like that only we can check for the other inputs also. For the input 0 1 0 the sum becomes 1 and the carry out becomes 0, and also for the other for the input 0 0 0 1 1 the sum becomes 0 and the carry out becomes 1. So in this way we can check all 8 different for different 8 inputs. So that's all from my part. Sir, I am done. Hello, Sangeeta sir. Hello.
Yeah, Anirban. Anirban?
Hello, Anirban sir.
You have put him to sleep or what? Can you call him? Oh, he has logged out. There's some issue.
So maybe some network
Vishal, just
issue.
call him. You have his number, right? Just call him.
Yes, yes, sir. I'm sorry. Okay, sure. He will come back in 2 minutes, within 2 minutes. Hello.
Okay, okay.
Just
Let's wait.
Hello.
Yeah, Anirban, yeah.
Yeah, sorry, sir. Actually, there is a network issue, so that's why I had to
Are you
go
in
back and.
IIT? Are
No,
you
no,
in
sir. I
IIT?
am. No. I am not at
Then it is
IIT.
surprising. Then it is surprising. Otherwise, it would not be surprising. Anyways, yeah.
Hmm. Okay, so I am sharing
Yeah,
my
you start.
screen.
Yeah, yeah.
So can you see my screen?
Yes, yes.
Okay. So good afternoon, everyone. So now I am going to present the multiplexer and demultiplexer part. This is a logic diagram. This is a logic circuit that is used as a data selector. So multiplexer is termed as a data selector and demultiplexer is termed as a data distributor. Now what happens to this circuit? So in the general block diagram, here you can see there are m select lines. Let me change this present pointer option. Okay, now you can see my pointer. So here you can see there are m select lines, and with that m select line, that means there are 2 to the power m types of combination which can provide you 2 to the power m input lines. Now what does this m select line does? So here you can see that if there is one select line, that means if one select line is used that has two different logic levels, one is 0, another is 1. So when this select line is set as 0, then a particular line is connected to the output, but not the other line will be connected. If it is set as 1, then only the second line will be connected to the output. So that means depending on these m number of selected lines, the number of the particular number of output will be fed, uh, number of particular input will be fed to the output. How this logic works in the internally. So I am going to the next slide. So here you can see the this is a example of 4x1 multiplexer. This 4x1 means there are 4 data input lines, and at a time only one input line will be fed at the output. So for that we need two select lines. So for these two select lines, there will be 4 combinations 2 to the power 2, which are 0 0, 0 1, 1 0, and 1 1. And for each of these states of these select lines, only a particular input signal will be fed to the output. So let's see how it happens. So we know that for any, these are the AND gate diagram, and this is a OR gate diagram. So for any AND gate, if any of the input of this AND gate is 0, then it will not pass through any of the out in data lines. So output will be 0. So to turn on these AND gates, all of these input lines should be higher. So let's see for the first case, 0 0. Now these are the zeros. If I see that these two lines which are connected to this bottommost AND gate, which are converted through an inverter, so 0 passing through this inverter will give you 1. Again from here also S1 is 0, and passing through this inverter it is 1. So at this bottommost AND gate, both the select line inputs come as 1, and we have I0. So that means the output of this AND gate will depend on only on I0. If you check for the other AND gates, at least one of the inputs will be 0. So let's see for the second one. S0, S0 and S1 both are 1, both are 0. So for the second case, S0 is coming through this inverter, getting it 1, and then it is fed to it. But for S1, it is directly connected to this AND gate. So that means S1 is 0 for this AND input. So therefore, the output will be 0. With whatever be this input line I1, it doesn't matter because this single input is 0. So it is 0. As well as for both I2 and I3, you can see at least one or two of these inputs, select inputs, will be 0, and for that the output will not depend on the input I3 or input I2. Now in this case there is a 4 input OR gate, and in OR gate we know that if any one of the input of this OR gate is high, that means 1, so the output of this OR gate will be 1. So for S0, S0 0 and S1 0, we see that bottommost AND gate will feed this I0 data to this OR gate, and all other data will be 0. So the output of the Y, output of this OR gate will give you this I0 data for the first state diagram, for the first state of this S0 and S1, that is 0 0. Likewise, if I go to the second state of this S0 and S1 control signals, if it is 0 1, we can see that this I1 is passed through this Y. The same logic you can see, if S0 is 0, then it is coming to this through this inverter 1, and it is fed to this AND gate, and S1 is 1, and 1 is directly fed to this AND gate. So that means the output of this AND gate will depend on this I1 data input line. And if you verify the other AND gates, again at least one or two inputs of this will be 0. So their outputs will not depend on the specific data line. So for the second state 0 1, this I1 is fed to this input of this OR gate, and then at the output this I1 is coming. Likewise for the other states of these control signals. So here this is how this for multiplexer works. For with these two data control system, with these two control signals, 4 data lines are controlled. Now I am going to say tell about you the demultiplexer. Here the thing happens differently. Here this for the multiplexer it was like a data selector, but here it is the data distributor. Here only one data line is fed at the input of this logic diagram or logic box, and depending on these control signals it will choose the output lines where this data input goes. So for some state of this control signal, this Y0 output will be equal to this input D in. For other state of this S1 S0, this Y1, and then so on. Now I am showing you the block diagram which is in the circuit diagram which is inside this demultiplexer box. This is here. Now you can see that this data input line which is fed to all these AND gates, and with the previous logic, if any one of the input of this AND gate is 0, then Y3 will not, that output of this AND gate will be 0, and it will not pass your data input. And this S0 and S1 will give you that at which instance, which of the output will be equal to this data line, data input I. So suppose for first case, S1, S0 and S1 is 0, 0. So let's see, if S0 and S1 both are 0, starting from the bottommost AND gate, you can see that S0 is again coming through an inverter, changing its state from 0 to 1, and it is fed to this bottommost AND gate. S1 is also coming through this inverter, changes state to 1 and then fed to this bottommost AND gate. So that means both the select inputs coming here, which are 1, and also the data I is there. So output Y0 will be equal to this data I. So for the state of S0 and S1 0, 0, only the Y0 surpass the data I, whatever be the data I is. And other outputs of these AND gates Y1, Y2, Y3 will be 0. You can verify the same way for the second of Y1, like S0, S1 both are 0. Then S1 is coming as a 0 for this one, then output of this will be 0. So it will not pass that I. So likewise for other states also, if I say that 0, 1, only Y1 will pass the input, others will be 0. For 1, 0, Y2 will pass, and for 1, 1, Y3 will pass. So this is like a data distributor depending on the states of these two logic control inputs, which are S0 and S1. Now I am going to show the VLab simulation for this 4x1 multiplexer and 1x4 multiplexer. Okay, so here the steps for the experiment is shown for 4x1 multiplexer and 1x4 demultiplexer. So I am directly going to the simulation part. So in that simulator, first I am showing 4x1 multiplexer. So in this 4x1 multiplexer, you can see there are 4 ICs are used, and first one is the inverter ICs. In 7404 hex inverter, you can see there are 6 inverters inside one single IC, but for 4x1 we need only 2 inverters, so that's why 2 of these inverters are used. Now there is one 7411 AND gate IC. These are the 3 input AND gates. So we, for 4x1 we need 4 AND gates. So in each IC we have 3 input AND gates. So one IC is totally used, and in the second IC we can see only one 3 input AND gate is used. And last one is the 4 input OR gate 4072B. Only one OR gate is used. Now each IC will work when a power VCC of 5 volt is set to these ICs. So that's why before starting the experiment you have to turn on this power switch. When it is red, that means it is switched off. So I am turning it on, that means it is switched on now. Here S0, S1, both the data control signals are there, and others are the data inputs. Now S0 and S1 both are 0. So here these outputs are coming Y. So let me see which for this one, which output will come. I am switching on the D0. So D0 is coming at this output for S0 and S1 when both are 0. Now you can add this in the truth table by pressing on the add. So when 0 0, the output is D naught. Now if I change the state from 0 0 to 0 1, so let me turn this switch on. Here you can see whether D naught is turned on, the output is not taking this D naught line. So if I turn the D1 on, so then you can see that D1 equals to 1 and the output LED turns on. Again you can add this. You can see that for 0 1 state the output will be D1. Now I am again changing the state of these two from 0 1 to 1 0. So S0 will be switched on and S1 will be switched off. So 1 0 you can see both D0 and D1 are turned on, but at the output the LED is not turned on, it is off. So that means no D0 no D1 is passing to the output. If I turn on the D2, then you can see that LED is turned on. So that means for this state 1 0, the D2 is going to the output. So again you can add it here, and for the last state both are 1 and 1. So I'm turning on the S1 switch also, 1 1. Again you can verify that D0 D1 D2 whatever be the state, the output will not accept it. So D0 D1 D2 both all these data lines are on, but there is no output. If I turn on D3, then the output LED will turn on. So that means for 1 1 state this D3 line is passed through the output, and you can add this here. So for 1 1 D3 output, and output value will be 1 because D3 is switched on, so that's why it is on. Now I am going to the demultiplexer one. So here you can see that 4 data selector lines. So the data is being selected depending on this control signal. In demultiplexer you will see the opposite functionality. Here the demultiplexer circuit is shown. The same 74113 input AND gates are used with one inverter IC. Here there no OR gate is used, as I told you in the slides. So again you can turn on this VCC, otherwise the circuit will not work. You have one data line and there are 4 output lines. So data line will also be switched on. So data line is on. Now you can see the select lines, both the select lines are switched off. So when both the select lines are switched off, this data is coming through this output Y0. Here the LED is turned on. So you can see that when the select lines state is 0 0, the data is passing through this Y0 output. All other outputs are turned off. So you can add this here. So you can see that when data D is turned on and the control signal states are 0 0, so the Y0 output will be D equals to 1 and others will be 0. If I change the state to 0 1, like it is turned on, it is turned off, it is turned on, like this, so you can see the same data is coming to this Y1 output, and you can add it here also to check this. Likewise, if I turn S0 1 and S1 0, you can see this output is turned on. So that means the data is passing through this output and all other outputs will be turned off. And you can add it here also. And for both the control signals 1, you can see this last output is turned on. And with that you can add the truth into the truth table. So this is how the multiplexer and demultiplexer works. So if you have any question, then you can ask us now.
Questions, students? Adder, full adder on multiplexer, demultiplexer. You have any question? Okay, so since there is no question, so Professor Bhattacharya, I think anything, do you have anything to say?
I don't think so. I mean, you have announced already the next lab dates, right? So I think there
Yeah,
is nothing to add.
next 2 weeks are like you have holidays in the next 2 weeks. So next lab will be on 26th. So that will be the last lab class. And of course, as we have announced, there will be a test after that. Okay, that will be announced on 26th. Okay, when it will be there. So anything else? So the assignment will be put up after 26th, but you will be given 1 week after 26th. Okay, so you have to submit the report or assignment, whatever you call it, in the first week of November for this experiment. Okay? Fine. So if there is nothing else, then we can conclude. Anything else? Anyone wants to say anything? Okay, then. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.